day, everyone. Thank you for joining this webinar session we have going on. I'll start with some housekeeping items, but just a reminder to everyone, this is our series on FlowTherm XT. And this is the third session that we have going on today, where we've had two previous sessions, but today we'll talk about PCB-level thermal analysis. Mario, if you could just go back one slide. Just some housekeeping items for everyone. As with the other webinars, please note that this is being recorded, so it will be made available for you afterwards. However, please do use the chat functionality to submit any questions that you have. And as we've been doing in the series, we will be answering them throughout. And in case we miss any or more details required, we will circle back with you by email. We'd like to thank you all for the level of engagement we've had. This has been a fantastic series with just the questions and the follow-up emails that you've all been sending. As we presented in the last session, the session before, excuse me, what we have going on right now is we have an evaluation, a complimentary evaluation that's available to all of the attendees. I know some of you already started it. We will be sharing the link again during today's session. So if you have questions while we're going through, you can ask us, but that will be made available to you shortly as well. So today, our presenters, we have Mario and Richard. So Mario D'Souza, he's a pre-sale CFD specialist at Maya. Most of you should have already seen some emails from Mario going back and forth. Mario brings over 6 years of experience in aerothermal analysis. In terms of industry expertise, there's quite a bit in terms of his background with automotive and healthcare, though he touches on a lot of different areas, and we're really excited to have him present today. I'm sure some of you have already seen him in action with the great questions he's been answering. In addition, we're excited to welcome back Richard Ozaki. Richard was the speaker for our first presentation, and he's back here with us today. So Richard is a thermal engineer with Siemens Digital Industries Software. He brings over a decade of experience, specializes in electronics, and does a lot of work in particular with FlowTherm and in relation to thermal consulting and electronics. So really have a great duo with us here today that will be bringing us through this presentation as we move along. So with that, again, just so you're aware, most people have seen this already, but this session is being brought to you by Maya HTT. So Maya is the leading provider of digital engineering solutions and top global partner for Siemens Digital Industries Software. The history of Maya comes from a strong aerospace background with over 3 decades in providing consulting and software. However, we have moved and have provided support for multiple industries and complex engineering challenges. There's been immense growth we're seeing in engineering techniques and challenges around electrification, electronics cooling in particular, which is what drove this webinar series coming together. And we're happy to have clients working on these kinds of cutting edge problems all over the world, and we support them through our offices in US, Canada, and the United Kingdom. In addition, we're covering just a small subset today of what Maya is able to do and provide help with. And some of you already inquired around this, but our expertise does range well beyond cooling. If you're looking at understanding a little bit more when it comes to design, industrial IoT applications, even in terms of applied AI strategy or product lifecycle management, these are all areas we've been helping in terms of understanding the connectivity or related to broader engineering or digitalization challenges. So please don't hesitate to reach out if you want to know how this series or what we're showing here ties into something broader, or if you have questions in these areas that may be arising on your end or with your team or with your organization. More than happy to put some material together for you. But again, today really our focus will be going with the electronics cooling theme in relation to this FlowTherm XT webinar. So with that, I think we're getting ready to get started with part 3. Really today we're going to be looking at PCB-level thermal analysis, and Mario and Richard will be bringing us through showing a workflow demo, going from CAD to electronics cooling, as well as a few other areas. So with that, I'm actually going to pass it off to Mario. Please take us away, and we look forward to having this session with you.
Thank you, Dan, for the introduction. So to begin with, let's speak about the challenges faced in the electronics industry. Over the past few years, electronics have increased in complexity of products, and it's across all the industry sectors. Miniaturization is forcing the mechanical and the electronic design flows to converge, and this in turn leads to increased power densities. Because of smaller packaging spaces as well, it is harder than ever to efficiently remove the heat, and this leads to performance and reliability problems. More importantly, there are safety concerns as well. Apart from the technical challenges, we see a few business challenges as well. With increased innovation and better performing products, we simultaneously see that the time and the budget allocated for the product design is shrinking, even if the competition is increasing every day. And also there exists a high pressure on getting the product out into the market on time, because being too slow, it may erode the addressable market that you would like to sell your product into. There are reliability requirements as well. System failures need to be found and fixed because they can cause costly downtime, product recalls, and also reputational damage. The, the, uh, the folks who attended the first session conducted by Richard, he explained to us clearly that 55% of the failures which are caused today are majorly by temperature problems, and we need companies to address these problems as of today. If companies do not address these challenges they face today and adapt their product development processes, it will definitely affect their bottom line through lost market opportunities and definitely damage to the brand. As you can see on the left-hand side over here, a major aircraft manufacturer had a problem of their battery pack exploding when luckily the flight was parked. So FAA went ahead and grounded all their flights, and the flights were recalled until the problem was fixed. Another example on the right, you can see where a popular phone manufacturer had their products exploding when the phones were charging. The cost associated with the repair and recall is definitely a lot, and additionally, the damage to the brand is even more immense. These are definitely extreme examples which you are seeing over here, but we can always learn from these examples. So in today's session, we will address a lot of these challenges. We will learn how we can use FlowTherm XT at any stage, be it from conceptualization to manufacturing, to improve the product quality, reliability, and time to market as well. So the agenda for today's session, we're going to introduce FlowTherm XT to you, an overview of the thermal design process with a traditional way of setting up a simulation, and then comparing it with the FlowTherm XT way of setting up a simulation for electronics cooling. We will then have a detailed session on the FlowTherm XT demonstration of a thermal simulation of a PCB and its components, in which we will look at the MCAD data, ECAD data, meshing, and post-processing as well. We will continue the session with design optimization within FlowTherm XT. And lastly, Richard will show us some of the successful industrial applications of FlowTherm XT. Simcenter Flotherm XT is a market-leading thermal analysis tool for electronics cooling. At the product's core is a 3D CFD solver which simulates conduction, convection, and radiation coupled with fluid flow for forced or natural convection. In one sentence, it's a specialized electronics cooling product line supporting design processes from concept to verification. Its primary and industry unique aspect is that its ability to support data evolution as a mechanical or a board layout changes are introduced into the product late in the design. FlowTherm XT is a unique software solution that delivers on interconnecting both MDA and the EDA design flows, and we will see this in a lot more detail in today's presentation. The software is CAD-centric and design and operation that has a configurable UI that supports the needs of design engineers and thermal specialists, and also they may not require access to all of the CAD functionalities. The product is focused purely on electronics cooling applications and has been built on 25+ years of innovative technology and FlowTherm, and utilizes the general power and sophistication of FlowEFD as an enabling technology for meshing and solving. Now let's have a look at the different levels in which FlowTherm XT can be used. For example, you can use FlowTherm XT at the IC package level, looking at the silicon and the substrate at the package level. The board and the system level, where you're taking your PCB and integrating it maybe into a larger system. We can look at the PCP and PCB in the chassis level. And finally, the rack and the environment level. This can be data centers where you have servers in a room with dedicated cooling apparatus. Simcenter FlowTherm XT has been designed basically for non-analysis experts to quickly perform thermal analysis, to guide product design and eliminate unfeasible revisions. Let's begin by understanding the thermal design process. We will be comparing the thermal design processes between the traditional and the FlowTherm XT methodology. So it's time for our first poll question.
Excellent. Great introduction, Mario. Let me go ahead and get that first question launched. So it should be on your screen now, and I'll just read it out for anyone having issues with it. So Which phase in the thermal simulation workflow do you find yourself spending most of your time? And you can choose more than one. Was it mechanical design, electronic design, meshing, solving and debugging, or post processing? So again, it's a relative answer, and we'd love to just get your perspective. And I think it'll help Mario and how relevant and the framing that will be used in relation to the upcoming part of the presentation. Great. We'll give it just another few seconds. Sounds like, for what it's looking like, most of these areas seem to have quite a bit of impact on timing. So I'm going to go ahead and close the poll. And again, people are allowed to choose multiple answers, and I think that's what's been happening. In terms of sharing it, you can see it. Sounds like when it comes to thermal simulation workflow, just about everything takes quite a bit of time. But we're seeing a lot of audience members, in particular, if we're looking at even the mechanical portion. I guess this is related a bit to your roles. And mechanical design meshing seems to take up the majority of the time, but seems like everyone has, or a majority of the audience members will have issues in almost each of these areas. So, Mario, I don't know if you can speak to how this relates to what you're seeing out there in industry and with clients, but I'll pass it back to you as you address that and continue on with the presentation.
Perfect. Yeah, Dan, this is what we see traditionally in all of our clients or all of our customers when they come to us. Most of the customers spend majority of their time in either meshing and pre-processing their mechanical CAD or their electronic design flow. So most of the customers spend time there, whereas we want customers to spend time where it actually holds value. For example, in the post-processing, creating design changes, creating new designs. This is where we want to take our customers to, and this is what I will be addressing right now. So to understand the process improvements that FlowTherm XT provides, we will first need to understand how a traditional CFD process integrates the MDA and the EDA design flows, and that's what we will have a look at it now. The first step is usually to create some form of geometry within the tool, then assemble the model by taking the updated data, and this usually happens late in the design. The native CAD geometry has to be simplified before it can be exported for use by the CFD tool. For example, it's exported in a neutral file format like STEP. Before that, it has to be cleaned, meaning all the problems of small gaps in the geometry have to be closed before it can be used for analysis. Similarly, the native EDA data also has to be exported, for example, in an IDF neutral file format. Components that are not important to the thermal design are usually filtered out to simplify the assembly. As EDA design tools usually work in 2D, information about the layer stack-up for the PCB has to be provided as well, and we need to provide the thermal models for the components that need to be considered in the simulation. The next step is meshing. Traditional CFD meshes the surface first, and then it meshes the flow space. And this is error prone, as features of the geometry can cause meshing algorithm to fail, necessitating more of the CAD geometry cleanup. And if it fails again, the CAD geometry must be further simplified, re-exported, and the cleaning step has to be repeated before the meshing can be reattempted. Meshing can also fail because of the geometry imported from the EDA system. In this case, there is little option but to re-export the native EDA after making some modifications in the EDA system and repeat the geometry preparation steps. Failures associated with both the MDA and the EDA design, EDA geometry can make meshing a very lengthy and a manually very intensive process. Once complete, the boundary conditions need to be prescribed to complete the definition of the thermal model. For example, the powers of the components which become heats, these need to be defined. It is then possible to solve the case. However, failures can occur if the mesh quality is poor. Maybe we have skewed large cell size differences, and this can cause the solver to converge slowly, or worse, it can cause it to diverge. And even if you're successful, it can result in a poor quality result. Post-processing is later needed on to interpret the results and finally form some kind of report generation to feed recommendations back to from the simulation team back to the design team to improve their design. The downside of this process is that it can take a long time to go through the cycle. By this time, the simulation model, it has become stale as the design has already moved on, and making implementation of any design recommendation is problematic. So let's compare the same design process with using FlowTherm XT. The create geometry step is the same as before. However, the geometry can be a CAD geometry created within FlowTherm XT, or it can be a smart part based. The assemble model step is compressed because FlowTherm XT can directly work with the CAD geometry so that the CAD can be imported in the CAD system's own native file format directly into FlowTherm XT. If required, unnecessary details can be removed by rewinding the features of the model within the CAD system. Similarly, the native EDA data can be exported as well. All of the processes incorporated into a new module, which we call the Flow EDA bridge, simplifying the preparation of the model. Component powers are also specified through the Flow EDA bridge, which then allows a fully defined thermal model to be read directly into FlowTherm XT. Meshing is compressed as well. We avoid all the problems associated with the traditional CFD meshing approach. In FlowTherm XT, we use what we call the object-based mesh controls and a Cartesian-based mesh system. This technology doesn't suffer from the mesh quality problems associated with body-fitted meshes. So as a result, the solution proceeds more quickly and without any convergence problems. The report is generated automatically as well, so the recommendations from the simulation can be fed directly to the design team, and this can happen in a very short elapsed time. The previous settings are retained by the Flow EDA bridge, so the EDA design updates can be re-imported, and any previous simplifications that you did to the MDA geometry can be repeated before the geometry is sent to the simulation. So this way, the simulation model can keep pace with the changes both in the MDA and the EDA design flows. Hence, subsequent simulation can be undertaken even faster. Let's have a look at some of the key enabling features of FlowTherm XT, and let's look at the workflow demo. We saw the comparison of the traditional and the FlowTherm XT method on a flow chart. Now we will have a look at the workflow demonstration of a thermal analysis of a PCB within an enclosure, and this we'll have a look at it in the actual tool so that we can actually appreciate its value. We can see some of the key features and functionalities on the left-hand side, each of which we will be covering in a little bit more detail. By the end, you will have a clear idea of an airflow and a thermal analysis of a PCB in an enclosure and some design optimization using FlowTherm XT. FlowTherm XT is a standalone thermal analysis tool, just like I just described. So the geometry can be imported into the software in a variety of file formats. It does not restrict you to one particular format. Assembly configurations and part modifications are supported as well. So once you have imported the geometry, you can create variants. You can also modify and simplify the geometry. You can assign thermal and flow attributes directly within the tool, such as materials, fan curves, and this is what you can see on the screen, and we will do it live on the tool as well. So this is how the GUI looks like within the tool. On the top, what we have is what we call the ribbon toolbar. This is going to basically guide us through the whole analysis process. We have the project manager on the left-hand side. So you can see that we have about 15 parts over here, which we have already imported, the casing and a dummy PCB. And as I click through the different bodies over here, you can see it getting highlighted on the screen. On the right-hand side, we have what we call the FlowTherm XT Smart Part Library. The Smart Part is divided into geometric and non-geometric smart parts. In the geometric smart parts, we have fans, heat sinks, cuboids, cylinders, and so on. So basically, this helps us to actually create the geometry in a very simplified fashion. We also have non-geometric smart parts, contact resistances, electrical conditions, flow devices, and so on, as you can see over here. So these are thermal and flow attributes that we are going to assign on the geometric smart parts or on the imported geometry. For example, we have a fan over here, which you can see. And today we are going to apply a flow device to this particular fan and assign a non-geometric smart part to it. So before we move any further, let's take a look at what are the attributes assigned, be it thermal or flow attributes that are assigned to this particular model. Since it's a fresh simulation, we don't have anything assigned over here, but as we move forward, we are going to assign each of these attributes and we are going to move forward. So I have already imported the model, but let's quickly have a look at the formats in which we can import our files in. Let's speak about it a little. So we have neutral file formats such as IGS or STEP and SAT files. All major 3D CAD platforms can export files in these formats, and we can import them within FlowTherm XT with no issue. We have file translators as well for solid edge assemblies, Inventor, NX, and also ProE Creo files. So basically, this file translator can translate these file formats into FlowTherm XT compatible geometry. We do support SolidWorks files natively, including all the parametric and the history-based modeling, which is used actually to create the SolidWorks files, which can be modified directly within the tool. Finally, we also have the PDML file format. Now, this is a FlowTherm XT proprietary file interchange format. These are commonly found by vendors such as IC modelers, which can be downloaded and you can directly use it within the tool. Jumping back to the tool. So we have a blank assembly over here with no attributes assigned. So let's go ahead and assign attributes of materials to two of these components, which is my casing as well as my cover. So this is the properties window, and we can, in FlowTherm XT, we have a library of parts which are associated with the electronics cooling industry. So for example, I'm going to go ahead and assign mild steel as my part over here. And once completed, you can see it reflect over here in the summary attributes window. So the next thing which I'm going to do is I'm going to create a detailed model of a fan. So I'm going to assign a flow device to the fan, which is a non-geometric smart part, as well as I'm going to save this fan so that you can use it at a later point of time. So firstly, before we begin, let's go ahead and assign material properties to the fan. So this is my fan. And so I'm going to go ahead and assign nylon because it's a low conductivity polymer. And we have defined the material properties for the fan. Similarly, I'm going to go ahead and define a non-geometric, non-geometric smart part, which is a flow device on this particular fan. So immediately it opens the property window, and you can see that firstly, we are going to go ahead and assign the outlet side of the fan, and then the inlet side. Once we have completed this, we need to assign the volumetric flow rate of the fan. We can do it in two methods. It can be based on a fixed volume, or we can base this on a fan curve. And this is what we're going to do. We are going to give some intelligence to the fan, and we are going to go ahead and assign a fan curve to this particular fan. So I'm going to go ahead and import my fan curve. So basically, a fan curve is nothing but it's for a particular pressure drop. It's a curve which defines for a particular pressure drop we are going to have a particular flow rate depending upon what pressure drop we have across the fan. So this can be imported in the form of a CSV file. It's fairly simple to do so. If you already have some details of the fan, you can import the fan curve and assign it to this particular fan. So now it's pretty much completed. We have defined, basically, we have gone ahead and defined the material property as well as the fan curve. So because it's a computationally efficient model, we have not modeled the interior blades of the fan. Rather, we have gone ahead and defined a fan curve. So now let's say that in a future point of time, this is a very common fan which you come across in your model. So what you can do is you can create a user library. You can drag and drop this particular part in the user library. Just like you can see, I have a couple of parts here. You can add this fan to the user library, and at any point of time, it's going to be available with all the details so that you don't have to recreate it. To reiterate, FlowTherm XT is MCAD agnostic. All of the 3D CAD formats are supported. We save time by preparing the geometry in FlowTherm XT using the geometric and the non-geometric smart parts. We definitely save a lot of effort by reusing the models in which we have within the user library. Before we jump into the next topic, which is PCB import and preparation, which is the main topic over here, I would like Richard. He's going to take us through the different types of PCB modeling and importance of each one of them. So Richard. Audio is yours.
Yeah, sure. Thanks, Mario. Yeah, just before I jump in, can I ask you just to turn your microphone up a little bit, please? You're a little bit quiet. But okay, so I want to talk about what is a PCB, first of all. Well, PCB stands for printed circuit board, and if you open up any sort of electronics that you might have around your house, you'll almost certainly find a PCB in there. And its main purpose is to electrically connect components together. You know, you're routing signals from one chip to another, going through resistors, capacitors, inductors. There's various components on a board that can be surface mounted or through hole. You know, most modern electronics are manufactured with surface mount components. And it's a combination of conductor and dielectric. Okay, so the copper, it's normally copper and FR4, which is a fiberboard material. So the copper kind of conducts the signals, the FR4 stops the signals. Okay, and for PCB, there's power and signal integrity requirements. Okay, you need to get certain voltages to certain components at a certain time, and there's all sorts of electrical simulations we can do as well. But another thing about PCBs is that also mechanically mounts to the enclosure. There's screw holes, there's mount holes. They can often be load bearing. The heat sinks in the top right image, for example, they are actually clipped to the components below. So mechanically, the heatsink sits on the component has been soldered to the board. So it is a mechanical load-bearing component within the electronics enclosure. And there are certain thermal design aspects that can be incorporated, right? Thermal vias, copper pores. You can play with the layer thicknesses. Remember, the PCB is a stack up of layers, right? Conductive and dielectric layers. It can be, typical PCBs can be 4-layer. They can go all the way up to 32 or 64-layer PCBs. They can be very, very complicated depending on the task they have to perform. And the PCB, essentially, it's a critical conduction path. You can use those electrical design aspects like vias to also conduct heat, because remember, copper is a very good conductor of heat. So, Mario, next slide, please. So we'll talk a little bit about PCB modeling levels. There's a few different ways that we can model PCB. So let's have a look at this example. This is called the BeagleBone Black. It's a competitor to the Raspberry Pi. And what we have here is what we call the thermal territory representation. So the PCB has been imported in very, very high fidelity. We have a very detailed QFN package. So here, remember from session 2, where John talked about very detailed IC models. Here's a detailed model sitting on the PCB. And then to ensure that we get the conduction paths, the thermal conduction paths correct, it's sitting on what we call a thermal territory, which is an explicit modeling of the copper within the PCB underneath that component. Okay, so we have a detailed chip, we have a detailed representation of the PCB under there. Next slide, please. Okay, so you don't have to model it in that higher detail, especially if you're early on in design phase. Maybe you don't have that level of resolution. The PCB team haven't laid out their boards or finished routing them even. So we can also model the PCB as compact or detailed. And I'll get onto this, but basically we can either do a volume averaging of copper within the PCB for the entire board, or we can do it on a layer by layer basis. So you can see here the layer definition, this image on the sort of the bottom right. You can see we've got, I think, up to 5 layers on this one. There's a varying amount of copper on each layer. And again, that's going to have knock-on impacts on the conduction capability of that board. But the important thing about compact and detailed is that there isn't any localization of the copper, right? It's smeared, it's averaged over the entire PCB or the entire layer. Next slide, please. Okay, so if we have a look at the difference in the results, you can see, we're getting, if we use a compact PCB, this is a like-for-like comparison. If we use a compact, we're getting maybe 56.7 degrees C. And if we go to a detailed, then we drop that temperature down to 54.4, right? So not a big jump in the temperature, but, a couple of degrees could make a difference. And that's generally the case. As you start to localize the copper and you start to put it where it's meant to be, then the temperature starts to go down because copper is spreading that heat a lot better. Next slide, please. So in the Flow EDA bridge, which Mario is going to explain next, we have the ability to model the PCB design in very, very high fidelity. Okay, so one of the options we have once you import the ODB++ file is to select individual nets in the PCB. A net is a copper trace that connects components together. Okay, you can select individual nets and mark those to be modeled explicitly. Okay, next slide, please. Alternatively, we can use something called a thermal territory. A thermal territory is, instead of selecting a net, we select a region around the component. So here's our QFN. We can select a territory size, an inflation zone around that component, and then select the depth that we would like to model the copper in explicit detail. Okay, so remember PCBs are made of layers, so we can choose the depth, how many layers that we would like to have this thermal territory in. Okay, so let's go to the next slide. Okay, so here's just a quick comparison showing different thermal territory sizes and, inflation sizes and depths. Okay, and you can see there is quite a variation in temperature here, but what we found in our internal studies is that it's important to get the depth. You get the most accurate results when you model the depth in the full, all the layers of the PCB going through to the bottom surface. Okay, and the inflation size isn't as important. So if we go to the next slide, you can see here just a comparison. So on the far left, we have a thermal territory with only going down 2 layers, and then over on the right-hand side, we're going down all the way to 6 layers, and you can see there's actually, almost a 15 degrees C temperature difference when you do this. So again, very important to check the sensitivity of your model. There's no hard and fast rule as to how big a thermal territory should be. It's one of these, sensitivity tests that you need to perform. And the general rule is, go the full depth of the PCB, and then vary what the inflation size is, and kind of find out for yourself how sensitive your PCB is going to be. All right, next slide, please. Okay, so we've talked about the simple board modeling level. That's the entire PCB averaging. Okay, then the compact, so that is the layer by layer averaging. Okay, and then we've talked about explicit traces and thermal territories. Okay, so that's where the copper in the board. So what's next? Okay, is there anything we can do better than that? Because simple and compact, those require next to no mesh to resolve. Detailed and explicit traces, they require a lot of mesh because we're creating these very fine geometries. So is there anything in between? So next slide, please. So the latest innovation in the Flow EDA bridge is the ability to use something called material mapping. And what this allows you to do is create a very highly detailed network assembly of conduction paths within the board. So we're not actually creating 3D geometry within the board, we're creating thermal resistances of the conduction within the board. Okay, and this is very easy to do because the board, the conductor, the dielectric is well defined. We don't have to worry about convection in the board. It's only conduction. So we can create like a matrix of conductances, a little bit like a Delphi component, but with a lot more resistances. And this is done automatically for you in the Flow EDA bridge. Next slide, please. Okay, so the material mapping allows you to either use the fine resolution, which will, on a pixel by pixel basis, will be copper or not copper, right? Explicitly how the PCB was designed. Or if you want to, reduce the solution time a little bit, then you can use the averaging technique where the copper starts to get smeared. You start to see the image get a bit more pixelated. You can control the resolution so that you have less thermal resistances, less thermal nodes within your PCB. And the purpose of this is to reduce calculation time, because there is a bit of overhead when using material mapping. So again, you're not restricted to that very fine. You can control it and create a good enough representation of the PCB. Maybe this central resolution of the PCB will give you 95% of the results of this ultra fine one, okay, but in a tenth of the solve time. I think that's a good trade-off. And again, that's something you need to kind of play with and understand the sensitivity of the modeling when it comes to component and PCB level. Next slide, please. Okay, so let's have a look at effect on the results. Okay, so we are going to be looking at a detailed PCB, okay, with average, the averaged approach. Okay, so we're looking at a layer by layer averaging. So this top layer's got 18.7% copper. So that means we've got, what's that, 82%, 81%, something like that of FR4, okay, and it's going to create a merge of those two materials to give an effective conductivity. In the second set of results, we're going to be looking at the material map with a resolution of about 50, okay, and we'll compare the results of these two. Next slide, please. Okay, so we have the detailed model on the left, we have the material mapping on the right-hand side, and if we look at the components in the top right, because we're averaging on the left-hand image, we're seeing some very defined hotspots in the top right-hand side of the board, whereas in reality, there is like a big copper concentration over there to spread the heat. So there is a temperature difference, like in the left-hand image, we've got a temperature of 79, and then on the right-hand image, we're down to 62. And that's a pretty big difference in temperature, 17 degrees C. That's huge in the thermal modeling world. So really, really critical to get the component and the PCB modeling right in your thermal analysis, because that's where the heat is generated. If your conduction paths and your convection paths are not correct, the rest of the simulation as you zoom out won't be correct either. What is good news is the main component, the component towards the left-hand side of the board, that doesn't actually change too much, 56.7 versus 56.0, that's acceptable margin of error, plus or minus 1 degree C. But the components on the right, where the conduction paths are critical, those need to have the detailed copper modeling or the material mapping. So with the material map, we do have a much lower mesh count. We're not meshing the geometry within the board, where it's a thermal node network. So it's just basically a matrix solve. So that does result in a much lower mesh count and a slightly lower CPU solve time as well. All right, next slide, please. Okay, so Mario, I'll hand it back to you, but that was just covering some of the aspects of how we can model the board and what sort of detail and resolution that we can go to. Thanks.
Perfect. Thank you, Richard, for the detailed explanation of the different methods in which we can model the PCBs and the board itself and the copper traces. So let's have a look at this actually let's continue our workflow demo, which was going on, and let's have a look at it in the tool. So like Richard described, there's a tool which we call the Flow EDA bridge for importing and preparing PCBs for thermal analysis. There are a number of, just like Richard described again, there are a number of methods in which PCB thermal modeling choices can be made. And this depends on basically the accuracy of the simulation that you need. We can also assign IC thermal loads and heat loads within the Flow EDA bridge itself. And let's have a look at this in the tool. I'm going to go ahead and import my EDA bridge and firstly import the PCB file. So you can see that we have a variety of file formats in which we can import our PCB. We have the ODB++ and the IPC I81B. These are the most common PCB formats that we have. We have the neutral file format, which is IDF as well. This time I'm going to use ODB++ to import my model. There's a reason for it. Using the ODB++, not only does the board shape components, locations, sizes, and heights come through. But most importantly, we also get the stack up information on the internal construction of the PCB. So I have my board imported almost over here. When I click through these different layers over here, I can click and it's going to get highlighted on the screen. We have the routing layers, the signal layers, the power planes, the ground planes, and so on. Let's look at layer 4 over here. We have 91% of copper in this layer compared to layer 1, for example, in which we have only 12% of copper. So layer 4 is going to be more conductive compared to layer 1. And so by basically FlowTherm XT reads this value, or it reads this value, and it's going to go ahead and create material properties for each of these layers. So now the second most important thing is filtering. So we can see that we have a lot of components over here. So we can use the filtering module within the Flow EDA bridge. So you don't have to do it in your CAD system. You can always do it within FlowTherm XT in the Flow EDA bridge itself. So let's go ahead and filter off the components which are not required. So by toggling on and off, you can see that we can filter off components which we don't need. For example, you have resistors, small capacitors, passive components, and our goal is not to model them explicitly. So by dynamically turning on the filter on and off, these components can get filtered off. So we can also filter based on the size of the component. For example, let me say that I want to go ahead and filter off components with footprint less than 10 mm. And we can see that all these components highlighted on the screen right now are smaller than 10 mm, and they're going to get filtered off, and they're not going to be included in our analysis. So if we include these passive components, what happens is size significantly increases, and in turn, it increases the overall solve time. So the next thing to do is, let's say, for example, let me close this. Let's say, for example, I have my high power CPU over here, which is U1. And if we look at the thermal modeling of this particular CPU, it's modeled as simple. So basically, the modeling method is simple. So it's just a simple block, and there is no internal construction or definition over here. So my goal would be to have a more detailed model. And so what I can do is I'm going to swap this particular component with the Intel provided model for accuracy. So it's going to be a lot more detailed rather than just having a simple block. So in my user library, I have the Intel provided model, and I can swap out the existing component with the more detailed component. And you can see over here, the swap is completed. And if you look at the model type, you have library detailed over here. Rather than before, it was simple. So now we have library detail. It means that the model is, it's a lot more detailed compared to a simple block. So the swap is completed. So now let me go ahead, we can go ahead and assign a power dissipation to this, which is maybe 8.8 watts. And you can see that this rolls up into the total power of the PCB. So you can see that you have the outline of the internal construction. You have the die, you have the substrate and the encapsulant. So with the correct material properties provided, because it's an Intel provided model, we can be very confident on the accuracy of this particular model. Let's take an example where we do not have a vendor supplied model. So what can you do in that case? Then you can still apply your own thermal resistances using what we call the 2 resistor model for this component U24, which is also another CPU which we have over here, a high power CPU. I'm going to use a 2 resistor model, and I can go ahead and assign my FETA JP and FETA JC resistances for both the components. As well, I'm going to assign a power dissipation of 1.2 watts. So you can see that this rolls for the total of the PCB board. So this is a very manual process. So we can use an alternative method. For example, if you have hundreds or thousands of components, what you can do is you can import a CSV file, and the CSV file is going to have the model type, the powers, the thermal resistances, all of the information that we may need for a thermal analysis is going to be present inside this power list CSV file. So you can see now that we have added all the necessary details. You can see the power roll up to be 18.322 watts. And this basically, it ensures the accuracy and the consistency of the data on the components which we have. So it's time for the second poll question. I'm sorry, Dan, if you could launch it.
Great. I'm putting it up now, Mario. I know there's a lot we've covered, but this question is actually going to be quite straightforward. So it relates to copper layers. So do you explicitly resolve all the copper layers under the high power components for accurate thermal modeling? Please select 1, never, it's way too difficult, 2, sometimes, and 3, always. This is a little bit of a loaded question, but I think we're going to be addressing how and why this happens. So let's give our attendees just another few seconds. It'll help in terms of what Mario is about to share moving forward. And as always, if you have more questions, please don't hesitate to let us know if there's any issues. We're always looking to make sure you're getting the best experience possible. Mario, we're still getting some feedback that it's a bit hard to hear your mic. So if you're able to speak up or make some adjustments, that would be very helpful.
All right. Is it better now, Dan?
It's better for me.
Okay,
yeah, we'll see if audience members have more to share. Okay, I'm going to go ahead and close this poll. So just a quick share over here. And 38% of our attendees saying that never when it comes to resolving all the copper layers. It's too difficult. And again, 12% said always. Sometimes it's a little bit in between in terms of 50%. So Mario, I think this tees up the next area of what you wanted to cover, but this should hopefully give you an idea as to what the audience has been experiencing. So with that, I'm going to close that poll, Mario, and pass it back to you.
Thank you, Dan. So yes, we do find a lot of our customers saying that it's difficult for them to explicitly resolve the copper traces and difficult to mesh later on as well. So let's see how simple it is to do in FlowTherm XT. So pulling back the tool, let's say that underneath my high power component over here, which is U1, which is named U1, I want to explicitly model the thermal layers. So what I'm going to do is I'm going to assign, just like Richard said, I'm going to assign a thermal territory underneath this component. I'm going to enable it. And I'm going to select the extent up to which I want this thermal territory resolved. So basically, a thermal territory is a zone or a region underneath a specific component which we want the copper to be modeled explicitly. So for example, there are some fairly thick thermal layers underneath this CPU component here, and it is critical. It is a critical conduction path through the board. So I would like to ensure that this is modeled explicitly, and so we'll create the geometry. So what FlowTherm XT is going to create this geometry for us and ensure that we are going to get the right conduction paths through this component. So I'm going to define the extent of which I want the copper traces resolved under this component, and later I need to define the depth unto which I want the copper traces to be modeled for this case. So I'm going to go all the way up to 6 layers over here. So the benefit over here is that you can create this yourself. The benefit of this is that it can be a very manual process to create it on your own. Once this is completed, once I model the copper traces underneath the power CPU, I can send this model back to FlowTherm XT. From the EDA bridge, we'll go back to FlowTherm XT with the detailed PCB. So to summarize what we have done so far, we have the material definitions assigned on different components that we have, thermal attributes assigned, and we got the total power defined as well using the CSV file. So let's look at the thermal territory which we have over here. So before that, let's have a look at the attributes which we have. We can see that what we define in the Flow EDA bridge gets reflected here. We have the material properties, the thermal properties, and all our powers, they are reflected over here. So now coming back to the PCB board, if I rotate it, you can see that underneath my CPU, high-powered CPU, we have the copper traces which are explicitly resolved. So let's have a look at this in a little bit more detail and understand it. So this is so what you can see is the copper territory underneath the CPU. We have, for example, the thermal layers. We have the traces. We also have the pads on which the CPU sits. So if you look at all these components, we have around 1078 parts over here, and it would be manually very difficult to model these copper traces. If you did it manually, it would take a lot of time. So FlowTherm XT does it automatically for you and assigns the correct material properties onto this part as well. So this is an automated process for importing and preparing PCBs for thermal analysis. So now we have a superior ECAD-MCAD collaboration, as you saw, for accurate PCB simulation, which is the core for a lot of electronic cooling applications. It is vital to get the component and the PCB right, as we all know. Using the thermal list, we can apply the component information in a fast and a very accurate manner, and it is an automated process. All of these, which you saw, most of them were automated processes within FlowTherm XT. Jumping on to the next module, once the geometry is completed and the user is happy, we can go ahead and we can set up and we can initialize the project and define the base parameters. So that's what we're going to do. We are going to create a FlowTherm XT project. So FlowTherm XT has a wizard-based project definition guide. So as you can see, the wizard, we have launched the wizard, and I'm going to create the project on the active assembly, our unit systems. And then you can either run in FlowTherm XT, you can have internal only flow or internal and an external flow. So in this case, it's an internal and an external flow because we are pulling in air into the slots on the side from the ambient. So for this reason, it's going to be an internal and an external flow. The solution type, it can be a flow and a heat transfer only, but if needed, you can run a flow only or a solid conduction only simulation. So we have 35 degrees as our ambient temperature. And then we have our gravity defined, which is going to be in the negative y direction. That is correct. So if you have, for example, the values of your overall domain size, you can go ahead and define that as well. So if you have the domain sizes, you can define domain sizes over there. So if not, you can just leave it as default values. It's going to take some default parameters of your the bounding box of your component, and then it's going to create a domain which you can alter later on. So now I have activated thermal radiation as well. So my next job is going to be to define the analysis type. Is it a steady state or a time dependent, which is a transient simulation? In this case, I'll leave it on steady state, but you have an option to do both. And then air is my working fluid, and aluminum 5052 is my working solid for the components for which I have not defined material properties. So when you click finish, what happens is it's going to size, the tool is going to size a computational domain for you. And this is, as I said, based on some default parameters, and you don't have to do it manually. So basically you don't have to create the extents. You don't have to subtract your components from the imported domain. So it does it automatically for you. So we have, let's say that we want to modify this or reduce the size of this domain. We can do this within FlowTherm XT itself. So by using these handles. So to summarize, we have our project, we have the materials, we have our PCB, and this is how we import and prepare geometry within FlowTherm XT. Basically, as we saw, the analysis project, it can be created at any stage in the process. So basically, you don't have to basically create it at the starting. You can create it at the end when you have imported all your paths, so that you don't have to re-import your paths in between the project. The summary is that it allows users to quickly and intuitively create a simulation environment with all the components and the project-based parameters, and it's all done in a single user interface. Hopping on to the next section, Simcenter Flotherm XT, it uses an immersed boundary Cartesian mesh for discretizing the domain into solid and fluid cells. The octree cell subdivision, the octree cell subdivision enhances the local result resolution, and the wall functions, they help us accurately capture the boundary layer using smart cells. And we will have a detailed explanation of all what I just said. So let's just say that I'm going to show my base mesh. Basically, it's an octree mesh on top of the model, and this is well before the mesh is generated. So what you can see on the screen right now, what you can see on the screen right now is the base mesh before any mesh or any cell subdivision has occurred. And this basically, it gives you an idea of how the final generated mesh would be even before generating the final mesh. So as you can see, the mesh is pretty much coarse in the far field area. The far field area as in the area between the component and the domain. Let's go ahead and zoom in near the edge over here of the fillet. We can see that we don't have enough cells to capture this fillet. Or if I show you the slots at the side, we don't have enough cells to capture these slots as well. So to capture these smaller features accurately, what we can do is we can assign grid refinements, and let's have a look at those. Just give me a second. Yep, so we have what we call the minimum solid feature size and the minimum channel size. So FlowTherm XT, it automatically detects both of these values for you based on some default parameters, and it refines, for example, the fillet or the slots on the side. Again, not having to enter these values makes it easier to generate a high quality grid with minimum intervention. So, yep, we have made sure that we can, let me turn off the mesh. So now we have made sure that we capture all the smaller features in a lot more detail. So lastly, the important thing to mention over here is FlowTherm XT is fully parallelized from mesh to solution. So just to summarize, the more the number of CPUs that you assign, the quicker you actually get your results. This is not a licensed feature. This is a part of the standard software package. So let's say that we have a heatsink over here which has fine ribs, and let's say that we want to have a fine mesh on the heatsink to capture all the details, also to capture the physics very well. So what you can do is, I'm in the properties window of the heatsink. We can go ahead and in the same window, we can activate localized meshing for the component. And also we can define a minimum solid feature size. It is pretty much done automatically, but in case you want to change it, you can go ahead and lower it if needed. So also I have ticked this box which says refine solid cells so that the solid cells are refined, but also you can refine the fluid and the solid interface for this particular heatsink as well. All right. So the next thing is for me to go ahead and show you the generated mesh. So I've completed the meshing for this model. All right, so let's look at the mesh in a lot more detail and know some of the features. So zoomed in near the corner over here near the fillet, you can see that we have a greater number of cells in this case. So for example, we have the base mesh over here, and this is split up, this cell is split up into basically 4 in 2D, or rather 8 in 3D. And then again, this cell is split up into 4, and then so on. So this level of transition can be done up to 9 levels of refinement to create exponentially smaller cells. The advantage of this kind of discretization is that the growth ratio is always maintained, which is 2:1 between the different levels of mesh. So basically, we will never have a sudden jump in the cell sizes because of this kind of discretization. The aspect ratio is always maintained as well. So for example, this base cell is going to have the same aspect ratio as the smallest cell in this particular model. This ensures basically the robustness of the convergence of the solver. Since the quality of the mesh is automatically taken care of, the user does not have to worry about the cell quality, and you don't have to worry about the divergence of the solver. Let's focus on the heatsink. As we can see near the tips of the heatsink, we have the software has automatically added more cells because this is where there's going to be a lot more convection involved. Another key thing to highlight is that smart cell technology within FlowTherm XT. Smart cells are found at the interfaces between the fluids and the solids. This is where the boundary layer forms and the convective heat transfer occurs. This is an example of a smart cell. We have a solid region which is sandwiched between 2 fluids on either side. This is basically a 3 control volume grid cell. There are planar surfaces separating the fluid, solid, and the fluid region, as we can see over here. This technology, in conjunction with our boundary layer treatment algorithm, allows users to have relatively coarse mesh whilst maintaining accuracy in the overall model. We can have multiple control volumes up to 12 within, for example, within this particular cell, you can have up to 12 control volumes. And this technology makes meshing very easy and very tolerant of dirty geometry. So you don't have to resolve fluid cells and solid cells separately. Because of the smart cell technology, you can have multiple control volumes or multiple solids in the same cell itself. As we saw, the tool is definitely tolerant of dirty geometry, overlapping geometry. Smart cell technology, the planar region, it takes care of the boundary layer, so you don't have to have a very fine mesh next to the boundary layer. It is handled automatically, and for very accurate results, the accuracy of the model is definitely not compromised. The automatic mesh generation with optional manual definition ensures that you're going to be creating the best of both the worlds, that is automatic and manual. To summarize the mesh capabilities and the meshing overview, it allows users to generate a high quality mesh without even being a CFD mesh generation expert. Once the previous steps have been completed and the model has been built, the mesh and meshed and solved, we can move on to the results visualization within FlowTherm XT. There are definitely a variety of ways in which you can examine the results, which we will see in detail now. We can also extract numerical data and convergence data, which is extracted from the solver. And there is also an option to automatically generate the report and also you can share it with your design team, and this can be standardized for standard outputs. So let's jump into the tool. So I have definitely solved the solution and kept it ready because we definitely don't want to spend time in simulating or solving at this point of time. So we can see, let's have a look at the numerical data over here. So we can see various graphs over here, and within FlowTherm XT, we have what we call as goals, and these goals are two types. Either you can have a monitoring goal, just to monitor, and a convergence goal. For example, let's take a look at the fan pressure drop over here. This is a convergence goal. You can see a small tick mark over here. It means that this goal has converged and the convergence has been met, and that is why the solver has stopped iterating. We can have multiple goals. For example, we can have another goal, which is a convergence goal, which is the fan flow rate over here, and you can see that it is fairly stable as well. Not only for the fan, you can have goals for different die temperatures, and you can make sure that the solver stops iterating only after these particular values have reached a converged value. So this is numerical data. So let's take a look at the visualization of different results. What we have over here, for example, let me hide my components. What you have over here is the planar plots. You can see the solid as well as the fluid temperature of different components that you have in the system. You can see the heat sink temperature and the fluid around it as well. And as well, definitely you can see the air which is coming, which is going to be relatively hot, which grabs heat from the heat sink and gets sucked out of the domain. So now you also have an option which is very good for post-processing as well. You have the probe option. So you can just hover, you can select the plot probe, and you can hover over the fluid region or the solid region to understand the different temperatures of the components over here. So as you can see, the ambient is at 35 degrees C, whereas the temperature of air which is coming out is 10 degrees higher. So it's easy to change legends as well. You can directly from temperature, you can move to speed or velocity, and you can see that the air, since the fan is an air mover and we have specified a fan curve, we have higher velocity of air exiting the enclosure through the fan, as well as you can see the slots over here, we have higher velocity of air entering the enclosure, as well as you can see, if I zoom in over here, you can see some separation zones over here where there is a sharp turn because of the pointed edge of the components. All right, so this is planar plots for you guys. So let me go ahead and hide these. Now let's take a look at the temperatures of the PCB and the components, now this is going to be surface plots on the components, which are going to be solid temperatures. You can have a look at this as well, and you can create a very it's very easy to create a detailed report, a good-looking report, and a standardized report because of having these different options over here. All right, so let me hide this, get my components back on the screen. So now let's take a look at the temperature of the heat sink and how it performs. So you can see that the temperature, the vane on the rightmost side is rather at a lower temperature compared to any other vanes of the or the fins of the heat sink. So we can definitely, there is a lot of scope to improve the design. That's what we understand over here. Let's quickly have a look at the heat transfer coefficient of the heat sink to improve our design in the future. So you can see that the heat transfer coefficient at the tips of the heat sink is higher, whereas it's almost equal to 0 at the center part of the heat sink. And to understand this better, you can definitely have a look at what we call the particle plots or the flow trajectories of the air around the components. And this is what you can see. So you can definitely see that as the air gets sucked in, there is a lot more recirculation, and then the air moves around the heatsink, but there is not a lot of air. If I animate this, you can see that there is not a lot of air which passes through this particular heatsink. So we do understand now that we have a lot of scope for basically optimizing our design. All right, let's get back into the presentation. To summarize, one more feature, I am sorry, which is a very, very good feature, which I would like to demonstrate. So you can definitely go ahead and create a report. And this is pretty much automated within the tool. So you can generate a report, and it can be either a goals report or a full summary report. You can have different kinds of reports depending upon your requirement. Let's say that I need a goals report, and you can add any screenshots if necessary, company logos if necessary, and you can create a document. In this case, it's a PDF document. And you can have all the information automatically generated within a report in just a matter of few seconds. You can see our fan pressure drop, and it's reached 100% convergence over here. You can see the values. Similarly, all the values which you would like to have, you can dump it in a report in just a matter of few seconds. Not only values, you can also dump screenshots of maybe thermal or flow attributes from FlowTherm XT, or even plots. You can definitely do that within the tool, and it's very easy to do so. To summarize, we can create plots to highlight key thermal performance metrics on the electronics. We can use numerical data comparatively to guide design decisions, and we can identify thermal bottleneck areas, just like we saw in this case. In this case, it was a heatsink which can be improved. The design can be improved. So by visualizing the results in FlowTherm XT, we can predict product performances and extract critical data on our electronics. So the holy grail of any simulation is going to be design optimized. So it's time for a simple poll question, question number 3, before we continue with our presentation.
I'll take over this. Dan's just had to step away. So here, do you run optimization studies to have the best possible design? So if you could select one, never, trial and error based on expertise, manually, for example, design of experiments, or always, and that can be automated within the tool as well. So we'll just give that a few seconds. Yeah, I agree with Mario. When it comes to any simulation, the more time you spend in the post-simulation optimization or the what ifs, that's really gonna give you the highest ROI on the software, because you're trying lots of different things. You can really explore and see how sensitive the model is to the inputs. Okay, I think that's probably long enough. I'm going to close the poll, and then if we share the results, you can see it seems like a lot of people manually do some sort of optimization or design of experiments to do what if studies, and that's good to see. and the lowest number is never. So again, great to see that people are doing some sort of optimization study. Okay, Mario, back to you.
All right, thank you, Richard. Yes, that's definitely true. It's customers these days are definitely doing design optimization studies, but in a manual fashion, and you can definitely go ahead and automate this process. There is a kind of a notion that it's difficult to perform, but I'm going to show you within FlowTherm XT, it's pretty much feasible and pretty much simple to perform. As I said, the final stage of any thermal design analysis story is going to be the design exploration stage. In FlowTherm XT, we can create manual variations or design of engineering studies of multiple input parameters. We can vary simulation or geometric parameters within FlowTherm XT and automatically, and we can create a table and then solve. And at last, you can go ahead and visualize the results of this table, which is generated. And that's what we're going to do in the tool right now. So, all right. So within FlowTherm XT, you can perform different parametric studies. You can have a manual variation study, design of experiment study, model calibration, or even an external optimizer. Model calibration. Make sure that you attend the next session. Richard is going to take us through that for sure. So I'm going to run a design of engineering studies, which we have already created and saved. And I'm going to take you through that. Because there are definitely a couple of results. I'm loading all the values. So let's begin with it. So firstly is what we go ahead and define our input parameters. In this two study, as you saw that the heatsink was not performing that great. So I'm going to run a design optimization study over here. I have two parameters. The first one is going to be my distance between this particular edge, which you can see, and this edge of the fan. So I'm going to vary this distance. So for example, in this case, on the screen, you're seeing the value is 50 millimeters, which is my base case. And I'm going to vary this value. I'm going to ask FlowTherm XT to vary this value between 25 and 150. So this is one of my input parameters. My second input parameters is the number of slots which are present. You can see these slots on the side. The top has 20, the bottom has 20. So this is the base value in this case. I'm going to ask FlowTherm to vary these slots between 10, the number of slots between 10 and 30. Now let's have a look at the goals that we have. What are the goals that we need to achieve? So my first goal is going to be the solid temperature U1, and my goal is to minimize the value of the power CPU, which you saw, which we modeled explicitly. So the value. So my goal is to minimize the temperature of this particular component, and the weighing factor or the cost function is 1. It means that it's the important goal that we have, which must be achieved. Similarly, I have another component, which is U24, which is also a high power component. So I am seeing that this is another goal. I want to reduce the temperature of this particular component, and the weighing factor is slightly lesser compared to U1. And we have specified our input and our output parameters. Now we need to specify how many scenarios do you want to run. In this case, I have run scenarios 10 plus 1, which is the baseline, so a total of 11 cases. And you can see the scenarios over here. On the top, you can see the values of the distance of the fan varying from one corner of the enclosure, and the second one, my second input varying, that is the number of slots, which is varied, and our results are obtained. So these are, the first is the temperature of U1, and the second is the temperature, basically the temperature of my component U24, which is present. So we have, as you can see, we have run 11 cases over here, or 11 scenarios, and you can see that the first one is the baseline, in which we have the temperature of 91.7. which is my baseline case. This is my temperature. So if you look at scenario 4, it's the worst performing scenario. That's why it's marked in red. So I can go ahead and make this my current scenario. So also I have hidden my heatsink. So you can see, you definitely can understand why is this the worst performing scenario. Just because the fan is far away from the CPU, or rather also the heatsink, not dry enough hot air, so that is it's performing bad. So let's look at scenario 11, the best performing scenario, and if we look at the values, I made this my current scenario. If you look at the temperature of U1, which is 77 degrees C, in the baseline we had 91. So this is a significant drop in around 13 to 14 degrees C drop in the basically 13 to 14 degrees C drop in the temperature. So basically, you can definitely increase the reliability of your product by running a optimization study like this, and also increase your clock speed as well. So right now you can see this is the best performing scenario 11 is the best performing design, arguably because it's the fan is directly placed in front of the heat sink, and it's definitely drawing in more air. So I can go ahead and load my results and have a look at let's quickly have a look at the flow plots around this case. So this is a very simple case, but you can definitely run optimization studies with greater number of scenarios involved and more complex studies, and get a really good optimized simulation within the tool itself. So you don't have to step out to another optimization tool. So if I show you the particle plots, there is definitely a little bit of recirculation in this case as well. So, but we definitely have a lot more air directly passing in through this particular fan, through this particular heat sink, and yep. So this is a greatly performing design, and we have a decrease in the temperature of the component U1. So let's say that you want to have a little bit more understanding. You need to understand the effect of each of these components in a little bit more detail. So let's have a look at that. So for that, what we have is we have the response surface modeler, or the RSM curve. Over here on the x-axis is basically, you can see the distance of the fan varying from one end of the enclosure, and the cost is basically your temperature. You can see that as we increase the distance from one corner of the enclosure, you can see the temperature of the power CPU drops. It reaches a stage where it's directly in front of the heatsink. That is where there is a minimum of basically you reach a minimum value of the temperature, and then as you move away from the heatsink, your temperature again increases. So if you quickly take a look at the other side, again, along the y-axis, I have the same thing, that is temperature, but along the x-axis is my number of slots. So you can see that as we increase the number of slots, the temperature reaches to a minimum value over here, and then as we go on increasing the number of slots, the minimum temperature or the performance becomes bad. So this way you can understand the different sensitivities of different components which are present in your model. To summarize, the benefit of performing a design exploration study is that we define the variant input and let the software find the best available configuration or a combination. We have the response surface plot for visualizing, as you saw, the input sensitivities. We clearly saw that the fan position was a lot more sensitive than the vent hole numbers. So the business benefit is that if we can find an if we can optimize our product, then we are going to improve the reliability of our design, and then reduce the number of respins that we are going to do by redesigning the product. And lastly, to summarize the key strengths, using the smart cell technology, as we saw, even a non-CFD expert can generate a great quality mesh even with a cluttered geometry. FlowTherm XT definitely has an intuitive user interface for preparing the simulation CAD geometry. We have inbuilt parametric study capabilities within the tool. We can run manual variations, DOE, model calibrations, and generate optimized design. This will help us generate a reliable product. We can, as John showed us during the second session, we can generate a detailed IC model using the package creator. Going forward, simulation of our electronic systems are only as accurate as the input data that you provide to the software. Thermal testing, it allows for accurate data to be generated, but also serves to calibrate and validate the simulations. And we will have a deeper dive into this topic, that is model calibration, in the next session, that is next Tuesday. Superior ECAD MCAD collaboration for PCB modeling. We can accurately model the copper traces using the Flow EDA bridge. This is efficient and very easy to do as well. We can create, move, and constrain paths together within the tool. You don't have to depend upon the CAD functionalities of another tool. You can do within FlowTherm XT. And lastly, we can go ahead and import FlowTherm projects and assemblies with no issues and perform the thermal analysis of the same. So now I'm going to hand it over to Richard to take us through some industrial examples which he's worked and gained success.
Yeah, thanks, Mario. So Yeah, sure. Just to talk about a couple of customers who are successfully using FlowTherm. So FLIR Systems, you're probably familiar with them for creating infrared cameras. So this is a new security camera that can be externally mounted. So it's got some pretty harsh environmental conditions. And what you can see is a plastic clamshell. This is IP protected, so there's no fans, there's no airflow allowed through here. There's only the natural convection within the box, which can be used to cool the electronics. And we were seeing very good correlation between physical test, in this case IR from FLIR, versus FlowTherm simulation. So they were seeing great correlation in the upfront design stage. Next slide, please. So yeah, you can see that they had a couple of different simulation models. They had, the early stage production design that could drive, for example, where the component locations were going to be and material selection. And then they had the late stage validation simulation as well. And that just goes to show how FlowTherm can be used early on and late stage to give you insight into your product performance. Okay, next slide, please. Next one is Continental AG. Very big tier one automotive supplier in the European region, and these days, electronics and electronics development within cars, even internal combustion engine cars, is approximately 60% of a vehicle development cost, especially with newer ADAS systems, self-driving systems. Everything is electronics these days. My new car's got like an electronic handbrake, even e-brake. So everything requires an electronics module to control that aspect of the vehicle. So next slide, please. So in this instance, they were using it for their ADAS. This is their forward-looking camera for things like collision detection, lane departure detection, and things like this. And when it comes to vehicles, the lifetime of the electronics is, you might own a vehicle for 20 plus years. It's going to be on the road for a long, long time. So it needs to be very, very reliable. It needs to have redundant backup systems in case something fails. So the requirements for automotive are a lot higher than consumer goods. So thermal, as we saw, is the #1 cause of failures. We need to get this right, and you can spend a lot more money on heat sinking and other exotic methods to dissipate the heat and get rid of it, and that's what Continental have done with their new ADAS camera design. Next slide, please. Last one, Visteon in Michigan. Again, if you've stepped into any new car recently, you'll see that all the dashboards are moving towards digital, right? No more mechanical dials, everything is LCD. And again, the same requirements for long lifespan, redundant systems. You can't have the gauges failing on you. That can be catastrophic. So if you go to the next slide, we can see that Visteon use and import their very detailed PCBs with detailed components using the Flow EDA bridge. They're able to then simulate what the temperatures and what sort of airflow is generated around the instrument cluster. And again, the goal here is to make this as reliable and as cool as possible to reduce field failures. Because, instrument cluster, you can't just swap out the PCB. Chances are you have to swap out the entire cluster, and that can be order of thousands of dollars to replace that if something fails, especially during the warranty phase. Okay, so that was just 3 examples. Just to conclude, Mario did a great job showing what the workflow steps of FlowTherm XT is, but really what you're able to do is get insight, right? We can see what the airflow looks like. We can see what the temperatures of the components and the PCB is like. And if you model things right, from the IC to the PCB and beyond, then you're going to be able to understand what the junction temperatures are, what the case temperatures of the components are. You can do what-if studies, optimization, and design space exploration up front before you commit to tooling and commit to board layout, okay? And it really presents a fully de-risked development from a thermal standpoint, okay? You can make those real-time design changes. The PCBs can be updated and replaced within your system quickly, just by editing the board. We can minimize board respins. If there's a big problem with the board, that can be highlighted before you've signed it off. We can eliminate multiple prototypes, get to market faster, and reduce field failures. That's really what we're trying to do with FlowTherm. So if there's anything I'd like you to take away is just think about electronics, even the smartphone in your pocket. there's a chip in there, there's a PCB in there. The better you can model it, the better that you can give inputs to modeling those things, the better your simulation is going to be. And that's really where FlowTherm is the market leader for thermal analysis. So next slide. That concludes the session here. I don't think we have enough time for questions and answers, but if you would like to send them to your Maya representative, we can get to those. But thank you very much for your time. This is number 3 in the hands-on simulate series. This is the PCB thermal analysis session. Next week, I'm going to be covering thermal test and validation. So up to this point, we've talked about simulation and some fundamentals. We're going to round this out with a test webinar, and we're going to go into a bit more detail and fundamentals on how you should physically test electronics. It's a lot more difficult than you think. So please register for that and attend that. That will be at the same time next week. And please look for the evaluation link in the chat window as well. You can go ahead and try FlowTherm complimentary. So the final poll, if you'd like to receive a free trial, please go ahead. And yeah, we can send you a link where you can sign up and use FlowTherm for a limited time through your browser. Mario, any other closing words?
Perfect. No, that's all. So if you have any questions which we have not answered, you can write a mail to me, and we will be happy to answer those. Thank you for attending today's session. We will see you next week.